Hi, welcome to Unit 3, Topic 2, Video 6. And in this video we'll be talking about vectors and geometry, but we're going to be doing collinearity in particular here, which is exercise 4F on the textbook that we're using. So let's have a look. Three or more points are said to be collinear if they exist in one straight line. So this is the best diagram I've got, but hopefully you get the point. A, C and D, here we go, there we go, are said to be collinear because they exist in one line. Obviously, we say three or more because any 2 points, well, that has a single line that connects them. So 2 points are definitely collinear. 3 points may or may not be collinear. In this case, A, B and C, for example, aren't collinear. The coordinates can be shown to be collinear if we recall that U is parallel to V, then U equals KV. So to show that A, B, C are collinear, we just have to show that AB is equal to some constant times AC, or some other variation. Maybe AB is a constant times BC, or AC is a constant times BC, for example. Both vectors involve A in the first one. That means that they're on the straight line, because we've got to be a little careful. If we show that two vectors, say these two here, which I'll call P, Q, and then this vector here, RS, so I say, oh, I can tell you that PQ is equal to 2 times RS, therefore PQ, R and S are collinear. Well, that's not true, because the other thing that we need is a shared point to show that they're on the same line. So if it wasn't S, but it was actually RP, that would then give you the shared point. Here we have A, B and C, and A is a shared point. So not only do we have two vectors that are parallel, but they also share a point, therefore they must be formed by 3 collinear points. So vectors as position vectors, I've just taken this diagram from the textbook, but how would we prove collinearity here? This is where we start to breach into that geometric form of vectors. So with this in mind, we can lead ourselves to a really interesting result. Let's start by considering this rule and what it leads us to. So first of all, we know that AC is equal to C minus A. How do I get C minus A? Well, to get from A to C, I've got to go backwards along A and then forwards along C. So it's C minus A. But I can rearrange this now and I can say, well, vector C, which is going to be common in the moment, is equal to A plus AC. But I know that AC is equal to M times AB if we're assuming that they're collinear. So let's make the assumption they're collinear, which will lead to a way of proving collinearity. Now we also know something about AB. So this is equal to A plus M, and AB is, to get from A to B, I have to do B minus A. B minus A. I can expand this and I get A plus MB minus MA. And then I can bring this together and look at it and factorize. So I get 1 minus M times by A plus M times by B. And I can write this down as C is equal to lambda A plus gamma B. And I can change this back to OC, OA and OB and I get this result. So it leads to OC is equal to lambda times OA plus gamma times OB. And we also have this part of the result, that lambda and gamma have to add to give 1, because of course lambda is equal to 1 minus M and gamma is equal to M. So 1 minus M plus M is equal to 1. And if that's true, then A, B and C are collinear. So what does this actually mean though? Let's forget about the lambda and gamma adding to give 1. What we're saying is, can we, to prove this, can we take the outside two vectors and do any form of what we call linear transformation of those, linear combination of OA and OB to make that middle vector OC? That's the question. Now remember, we can always change these values. It doesn't have to be AC and AB, it could be AC and BC. So it doesn't even have to be OA, OB and OC there. This could be OA and then OB and OC. Now, once we've proven we can do a linear transformation, do the values of lambda and gamma, that's a sigma there, I might just change that guy, do the values of lambda and gamma, add to give 1. And additionally, if lambda and, I've gone back to front here again, so getting a bit confused with my notation. Lambda and gamma are between 1 and 0, then C is between A and B. That's the other interesting result we get. So obviously these two could be 0.4 and 0.6, and then C will be in between. But if they're 2.7 and negative 1.7, well then C will be somewhere towards the 2.7 beyond it, over here maybe somewhere. So we get some interesting results out of this. So here we go. Collinearity is obvious in 2D, pretty much, unless you draw a bad diagram like I often do. But it isn't always obvious in 3 dimensions. 3 dimensions makes things a lot trickier to visualize. And so unless you can really get behind the 3 vector points, then you can't really tell if they're collinear. They're just going to look randomly on a plane. So we can't assume anything. So let's have a look at an example here, which I have done. So let's have a look at an example. Given that OA is equal to this vector and OB is equal to that vector, determine the vector OC such that A, B and C are collinear. For your particular vector, determine AB, so the magnitude of AB as a ratio to the magnitude of AC. So this is interesting because I'm given 2 and I need to find a third. Now I'm not going to try and draw these, but just imagine I did do a little bit of a sketch over here and it's 3 dimensions. Well then this is O. A is going to be out here and B is going to be maybe back there, and it will mean that C could be here or here or here or here or maybe beyond, there or there. So C could be anything. Remember, all that we need is for our chosen lambda and gamma to add, so the sum of those two to be 1. So let's have a look at how we go. I'm going to determine OC such that A, B and C are collinear by actually just choosing my lambda and gamma. And that will give me an answer. So I'll just zoom in on this. So remember, I've got OC will be equal to lambda OA plus gamma, that's lambda again, OB, and I need lambda and gamma to give 1, so let's make lambda equal 2 and gamma equal -1. That sounds like fun. And so we get this, OC is equal to lambda times by 3i plus 2j minus k plus -1 times by 5i minus j plus 3k. And so now expanding and solving this, well, I'm going to sort that lambda, I just said this, 2, I get 6i minus 5i plus 4j minus, plus j, that's good, and then minus 2k minus 3k, and I can simplify this, it gives me I plus 5j minus 5k, sorry. And so there's my vector OC that is collinear with, well, C, point C, which is collinear with A and B. And I can go through and prove as I need to. Now, of course, I'm asked to find the magnitude of AB as a ratio of the magnitude of AC. So remember here that we said AB, this is our initial premise, is equal to M times AC. So basically, if we can find M, well, we're good to go, aren't we? So let's aim to find M now. Well, I can tell you a nice pattern exists, but I think we're going to do this manually to start with and see how it looks. So remember, AB will be equal to, if we go back, or actually if I sketch my diagram over here, AB, which is going to be that vector, and we'll call this point C, so A, B, C. AB will be OB minus OA. So there we go. OB minus OA, which I'll do pretty quickly, but we've got OB and OA. OB minus OA will be 5 minus 3, negative 1 minus 2, and 3 minus negative 1, which will give me 2I plus, actually minus 3J, and then plus 4K. And the magnitude, therefore, of AB will be equal to, it's not going to be pretty, I don't think, but this is 4, that squared is 9, making 13, that's 16, so the square root of 4 plus 9 plus 16, I'm cheating a little bit, and that is, of course, the square root of 29. And then we're talking about AC. So AC is going to be equal to OC minus OA. And OC minus OA, again, I'll do this quickly, is 1, so I'll just highlight the calculation I'm going through. 1I minus 3I is negative 2I. 5J minus 2J is, let's move down, plus 3J. And then negative 5K minus negative K is negative 4K. And maybe you're spotting where this is going to now, but AC magnitude is equal to the square root again, 4 plus 9 plus 16. It's got a root 29. And so therefore the magnitude of AB in ratio of the magnitude of AC is equal to root 29, root 29, or 1 to 1. Now that's an interesting result, which actually does stretch a bit beyond this, but it's also beyond the syllabus as a reference point. But of course, you know, you can do all the elements of this, so there's no reason why it couldn't come in as a question, but it is a nice result. If you extended this, and I encourage you to consider doing this, to have a play around, you could find a nice little pattern and maybe come up with OC, that point, by picking a nice lambda and gamma value to get the ratio to be root 2 to 1. But I'll leave you with that to play with if you want to. Anyway, that is the end of our lesson for collinearity. I hope it's gone well for you, and all the best.